So in this problem, we're given a situation that looks like this. We have a man pulling on a rope that's connected to one pulley, and then another pulley, and then to the ceiling. And the second pulley is connected at its axle to a mass M. So for part A, we're asked what the force that the man has to apply to the rope is, such that the little mass M will just barely lift off the ground. That's actually not the exact wording of the problem. The wording is, what force does he have to apply to start lifting the block? But those two phrases have the same meaning. So all we need to do is make sure that the tension force in this rope is exactly equal to mg, and this block will just barely lift off the ground. So first, I'm going to draw isolation diagrams for each of these pulleys. The isolation diagram for this mass is fairly easy. It's just the tension force and then the force of gravity. So I will leave that one out. But for these two pulleys, I'm going to start with this is pulley 1, and then this is going to be pulley 2. So for pulley 1, we have some force going up that I'm not going to label quite yet. We have the tension force in the rope, and then since the rope is massless and will not stretch, the tension force on the other side has to be the same, which means that this has to be 2T pulling it up. Now for pulley number 2, the rope is still stretchless and massless, which means that this tension has to be the same as that tension, which means that this tension has to be the same as that tension, which means that then when this is mg, because remember, we wanted to just barely lift that mass off of the ground, so this force downward has to be exactly equal to mg. This tells us that if the mass is just barely being lifted, that means it's not accelerating. Then we know that the sum of the forces is equal to 0, is equal to, we're going to define upwards to be positive, 2t minus mg, which tells us that mg equals 2t, and t is equal to mg over 2. Now for part B, we're asked that if the block is raised a distance h and then brought back to rest, what will its change in energy be? And all this is it's a gravitational potential energy question. Its initial kinetic energy is 0 because it starts at rest. Its final kinetic energy is 0 because it ends at rest. But its potential energy has changed by an amount mgh. No other energies have changed, so that's its change delta E. Delta E is just equal to mgh. Now for part C, we're asked that after it's been raised a distance h, how far has the worker pulled the rope? And to illustrate my answer, I'm just going to draw a little picture. So imagine this rope having not moved at all. But this pulley has to have been raised a distance h in order for the mass to raise a distance h, because this rope will not stretch. So if this pulley's been raised a distance h, then this distance is h, but this distance h on the other side of the rope is also going to be that same length. Now since this situation can't actually happen because the worker has to be continuously pulling on the rope so that the rope is always supporting the pulley immediately at the bottom, all of this slack has to be pulled away, and that's exactly 2h, a length of 2h worth of rope, which means that the worker has to have pulled in that amount of rope in order for this pulley to still be taut against its rope. So the man has to have pulled a distance 2 times h. Finally, for part D, we're asked what the work that the man will have done during this time period is. And that's just going to be the force times the distance over which it was applied, which is force times distance is equal to mg over 2 times 2h, because he pulls the rope a distance 2h. And so the worker does mgh in work, which is exactly what we would expect, because that is the change in energy of the block. And so mgh in work must have been done in order for the block to have been raised that distance.